All right, so I decided to do this recording through Zoom. Hopefully everything works well. This is the second question on the study guide for quiz number 5. We have basically a building in Texas that's kept at a constant 20 degrees C all summer long. And this is during a time when the average outdoor temperature is 30 degrees C. The building has a ventilation system. It continuously vents 50 liters per second of cool air. And the electric cost to keep the building at 20 degrees C is 15 cents per kilowatt hour. Assuming atmospheric pressure is 100 kPa, find the following. Part A, mass flow rate of the air leaving based on the inside temperature, right? So you can base a mass flow rate on for a gas, right? If you know the volumetric flow rate, you need to know some temperature. So you're going to base it on the inside temperature here. The amount of energy in kilowatts to cool the makeup air coming in from outside. And you can assume dry air. So the idea here is we're just ignoring the effects of moisture. The cost of the cool air vented out per month in the summer. So here we're going to assume 30 days per month, and we want that answer in dollars per month. So let's start this. Now, the first thing we can assume here is that air is an ideal gas. So let's work with that assumption in part A. Let's see, take air as an ideal gas. So if I do that, I can write, PV equals MRT. Remember, your thermal textbook uses a mass instead of a mole, right? If I take this whole thing and divide by time, 1 over time, I get a rate, right? I get PV dot equals M dot RT, right? It doesn't make sense to take pressure per time or temperature per time or gas constant per time, but volume, right, per time is volumetric flow rate. Mass per time is mass flow rate. So here I can rearrange this and find M dot equals PV dot over RT. And we know the volumetric flow rate, we were given that is 50 liters per minute. Now, I do need R. R is equal to 0.2870. And the units on this are kPa meters cubed per kilogram Kelvin. And this comes from table A1. Let me show you that real quick. A1. So here's air. And the gas constant is this 0.2870. Now notice the gas constant's got kilojoules per kilogram Kelvin up here. But if you look at the little asterisk, if you go to the bottom, it tells you the unit kilojoules per kilogram Kelvin is equivalent to kPa times cubic meter kilogram Kelvin. So that's where we got that from. All right, so it should be relatively straightforward to get a mass flow rate. The mass flow rate here is, let's put the numbers in and see what happens. 100 kPa, right? This is atmospheric pressure. So let's look at these terms. We got pressure, which is atmospheric. The volumetric flow rate is 50 liters per second. Now, underneath, we've got R and we've got T. So 0.2870. Look at the units on this. kPa meter cubed kilogram Kelvin. Do you see liters anywhere? Not yet, right? And then the temperature is going to be 273 plus 20 Kelvin, right? You need to use the absolute temperature in the ideal gas law. So I have kPa, I've got Kelvin. Kilograms, I want kilograms, and I want seconds. I've got liters here. I've got to convert liters to cubic meters. And the conversion factor for that is 1 cubic meter is 1,000 liters. All right, so you need to know that. In fact, I think, yes, I did. I put that on the conversion sheet. Constants and conversion sheets that's attached to this quiz. 1,000 liters is 1 cubic meter. So here you wind up with the mass flow rate is equal to 0.0595 kilograms per second. That's part A. All right, part B asks for the amount of energy to cool the makeup air coming in from outside. Again, assuming dry air. So we're just taking that it's pure air and there's no moisture in it. All right, so maybe I should have changed this from Texas to, like, I don't know, Nevada. I think Nevada is much drier. All right. So let's look at the open system energy balance here. And we're going to draw, let's see, I'm going to draw a diagram first. I'll draw it over here. I've got this pipe. So this is cool air in to building. Right. That's at 20 degrees C. And this is air from outside. And that's at 30 degrees C. Right, so somehow I need to cool this air down. Now, I also have mass flow rates, right? M in and M exit. All right, so we're looking at basically a cooling unit here. Very simple schematic, obviously, right? And I've got a control volume here in which I can see I've got Q out. So this is what it looks like if you want to set this up. And remember, MI, the mass flow rate in is the mass flow rate leaving, right, of cool, dry air. So use open system energy balance. And let me write that out for you. I'm going to start with, so let me write all these terms and we'll go through them all. What do I have? A mass flow, H. So I'm using I for inlet and E for exit. Oops. All right, so what do I have? First of all, if I look at what I drew, right, I definitely have heat leaving the air from my control volume. right? But I have no heat going into the control volume, so that's 0. I don't have any work in or out of this control volume, right? I'm doing some kind of cooling. It's probably just a heat transfer. So there's no work in or out. All right, so this whole term is 0. I have enthalpies of each stream going in and out. I don't have any change in kinetic energy, so no change in velocity, right? No delta V, so kinetic energy equals 0. And then the same thing here, no elevation change, right? No delta Z, so delta PE equals 0. So I'm basically left with negative Q out, some rate. Oh, I forgot to make these rates. Sorry, guys. This is a mass flow rate, so these should all be rates of heat in or out. So this is the heat, the rate of heat out, negative, right, plus M HI minus HE equals 0, right? That's the equation I'm left with. I can rewrite this. If I look here on my formula sheet, for an ideal gas, the change in enthalpies is equal to the average heat capacity or average specific heat times the change in temperatures. So let me make a note of that here. Note for ideal gas. HI minus HE equals CP TI minus TE. And the CP for air is 1.005 kilojoules per kilogram Kelvin. And this is from table A2. Oops, gotta move that up. Let me show you A2. Appendix A2, air. It gives you the gas constant again. The specific heat, 1.005. So this is C sub P, specific heat at constant pressure. So 1.005. And the pressure is considered constant for this scenario. All right. So that's the specific heat. So we can rewrite this. I'm going to substitute this in for TI and TE, for HI and HE, and I'm going to take this to the other side. And we can write Q out equals MCP TI minus TE. Right? That's just the negative sign disappearing. So you wind up with, let's see, 0.0595. I'm going to put the units in a minute once I put the, what was my CP? 1.005. And our temperature change, remember, delta T in Kelvin and Celsius are both the same. So here I'm going from 30 minus 20. All right, so the units on these are, this is kilograms per second. I've got kilojoules per kilogram Kelvin. And here I've got basically Kelvin or Celsius, doesn't matter, it's a delta, right? So I'm going to be left with Q out equals 0.05 kilojoules per second, or 0.60 kilowatts to cool the makeup air, right? That's what's being done here. You know, I don't think I pointed this out. It's the building is venting 50 liters per second of cool air, right? In order to make that up, right, it's got to suck in warm air. So you're cooling air from outside to, to add to the building as the building loses its cool air by the ventilation system. So this is part B, the amount of energy to cool the makeup air. All right, finally, part C is the cost, right? So the cost, so what's the cost of the cool air vented out per month in the summer? So the cost of cool air vented, right? Cool air vented is equal to the cost to cool makeup air, right? This is why your parents are always yelling to close the door in the winter, and then again in the summer when they turn on the AC, assuming you have AC. All right, so the cost is just going to be, we've got 0.60 kilowatts, right? We know that it costs us 15 cents per kilowatt hour, right? So let me write that one down, 0.15 kilowatt hour, dollars per kilowatt hour. Now, we want this cost per month, right? Let's make this cost per month. We have 24 hours in a day. That's going to get rid of the hours, right? So now we'll have kilowatt days. And then we have 30 days in 1 month. Right, because this is kilowatt hours. We want to actually multiply by, so we want to get hours up here per month. So here we have, if we do this math, we wind up with $64.8 per month. All right, so the cost, $64.8 dollars per month. So that's how you do the problem. Notice the kilowatts cancel, right? The hours cancel, days cancel. We're left with just dollars per month. So there you go. This is why it costs money to keep buildings up. And you know, actually, this is interesting with you know, the whole COVID thing. People are talking about, well, you know, improve air circulation and get the air through HEPA filters and get more air changes per hour. But that's also going to raise your energy bill as well. So if you're a business and you want to sort of make your place safe for you know, safe for COVID, and you want to do more air changes per hour, well, you're going to either wind up spending more money on heat or air conditioning or HEPA filters. So yeah, that's the problem. There'll be a similar one on your quiz. The one on your quiz will actually be, let's see, this is a building being cooled. I believe you will have something being heated on the quiz. I can't be sure, but let's see. And building is, yes, it's heated in winter. So you should be able to do this both ways. It's not going to rack your brains too much. Thanks for watching.